Welcome back. So let me continue from where I was. Yes, so this one is the simplest differential equation. And why do we need that? Well, as you see, this is defining the growth rate of x, right? So let me remind you again the solution. So when we have x dot t equals alpha xt, when we solve this, what we found is this general solution. Okay. Now, what do you see here? Well, if t is equal to 0, suppose that the initial period is 0. So let's define history starting from some initial point 0. Then what do I have? x0 must be equal to a times e to the alpha times 0. In other words, it must be equal to a, right? So what do I know? The definite solution is this. Now realize that by solving the equation, by solving this differential equation, I find the time path of xt. Okay? And this time path is in the meantime, showing me xt as a function of time. Okay? In that sense, it is a solution of this differential equation. And also realize that this is linear, right? Why? Because the derivative is a linear function of x. Okay? And from a linear differential equation, the time path that we found is exponential. Okay? So that's a typical outcome of linear differential equations of the first order. So once you solve it, you find that the solution is exponential. So how do you draw it? Well, very simple. T on the horizontal axis, xt on the vertical axis. So there is this initial level x0, right? And then there is this exponential growth path of xt. Now, obviously, from the very beginning, just by looking at the differential equation itself, we realize that the growth rate is constant and it is equal to alpha, right? So growth rate is at any point in time is approximated by this. So the change is approximated by this, of course, derivative, right? So if you take the derivative, it is alpha xt. So this divided by xt then gives you the growth rate alpha. Okay. Hacer, hangi aşamadayız?
Hocam bu defa daha iyiydi. Yetişebildim size. 1-2 dakika oynadı sadece.
Okay, all right. So let me then continue. Now, what I want to show you is the discrete time version of this. Okay. So now, suppose that time is discrete. And let's focus on a similar problem. Now, what I'm going to write is a difference equation. Okay. Let me actually do that. So what you see here is a difference equation, right? Why? Because now delta xt plus 1 is a function of xt, right? So how do we solve this? Well, there's a very nice, so this is again linear, as you see, right? Because this part is linear in X, right? So once again, I mean, it's very easy to solve. What we use simply here is called the iterative technique or iterative solution. Now, if I know this, I can write this differential equation in this simpler way. Okay. Now realize that this is true for all t, right? So suppose once again h is starting at 0 and going to positive infinity. Okay. Now I have x1, which is equal to 1 plus beta x0, right? Then x2 will be equal to 1 plus beta x1, and x3 will be equal to 1 plus beta x2, and that goes on, right? But now I can write x2 in this way, right? 1 plus beta. Now let me replace x1 with this. So I have 1 plus beta x0. Okay, now this one is x1. Okay, so eventually what do you find? You find 1 plus beta square x0 here. And if you do that for x3, if you iterate one more period ahead, what you have will be 1 plus beta to the third power times x0. If you do that for the fourth period, you're going to have 1 plus beta raised to the fourth power times x0. And that goes on. So you realize there is a pattern. So what is that pattern? Well, you have xt equals 1 plus beta to the power of t times x0. Now, once again, you find the solution, right? Why? How do you know this is a solution? Because now xt is defined as a function of time. This is the domain, right? This is the domain, and there is some real number at the end. So this is time, right? This is your history. And for each t, since you know beta, you have the solution. Okay? You can again draw it, but be careful now, because now growth is defined for discrete time periods. So you have 0 here, right? 1 here, 2, 3, 4, 5, and that goes on. Okay? So you will have some x0, some x1, some x2, some x3, some x4, etc. Okay? And obviously, again, the growth rate depends on the beta, right? How do I know that? Well, the growth rate is beta, right? From the difference equation itself, you realize delta xt plus 1 divided by xt is equal to beta, okay? So beta is the percentage growth rate of x, and 1 plus beta, of course, is the gross growth rate, as we did before. Okay? So that's very simple. That's right now, I showed you simple linear difference equations and simple linear differential equations that define processes that have fixed growth rates. Okay? In both examples, in both cases, the variable x exhibits exponential growth, okay, at a fixed rate. In the differential case, the growth rate is alpha. In the so it was an instantaneous growth rate, obviously. And in the discrete time case, the growth rate is beta, and beta is periodic growth rate from one period to the next period. Okay? So that's all very simple. Of course, there could be much more complicated growth mechanisms, but For now, that's good for us. Okay. Now, why do we need both of these, right? Why do we need both the continuous time and the discrete time? That's a question you might be pausing at this point. So let me explain. The simple reason is this. Continuous time and discrete time versions of analysis serve for different purposes. Okay. So if my purpose is to write a simple theory, okay, if I want to write a simple growth model to investigate theoretical mechanisms, continuous time is most of the time much easier than the discrete time model. Okay, so from a theoretical perspective, most of the time, again, there are some exceptions, but most of the time, continuous time model is much more easy to handle. Okay, because solving integral equations are easier than solving, summation equations and other stuff. Okay. So what's the purpose of using discrete time models? Well, if I want to do empirical analysis, okay, if I want to go to the data sources and download the data, that data is always periodic, right? Because GDP data, employment data, capital stock data, they're all sampled and observed at certain frequencies. Most of the time it is quarterly, right? I mean, in long run growth, we look at usually annual to 5-year to the 10-year data. So we want to focus on changes that occur from medium to long run, obviously. But for business cycle analysis, we can also look at quarterly data as well. So the highest frequency is, of course, quarterly for the GDP data. So as you see, they are both relevant depending on our purpose. If you want to do theoretical analysis, and we're gonna do some theoretical analysis, so you need the continuous time definitions. And we also do some empirical analysis. We're gonna look at some of the data resources. So we also need to use the discrete time tools as well. Okay. Now let me show you one simple application. Okay. Now suppose that you want to study the Turkish economy. Okay. Turkey. Now, there's this data source called Madison database. Okay. The most recent update, I think, is 2018. Okay. You can find this data online. So Turkey has some data, I think, starting at 1820s. Okay. So starting at the Ottoman period. Then it goes on with some jumps. Since 1923, there's an uninterrupted series running to, I guess, 2017. Okay. Now this data is real GDP per capita. Okay. And here, basically, we are looking at international dollars. Okay. So we want to correct both for the Turkish inflation, right? So it's not in Turkish liras. Also, we're going to look at the purchasing power parity differences across countries, right? So we want to take into account the exchange rate. So this data comes in a form that you can compare different countries. So there are two different versions actually. In one series, you can compare countries with each other. In another series, you can compare a country's past and present. Okay. Now that data is coming in an Excel file, right? So suppose that you have the Excel file here, all right? So you have the columns, okay, and then you have the rows. Okay. So now what you can do is this. You can define a T here So t, let's say, starting at 1923. Okay. And it goes on like this, right? 25 and goes on like this. Then here you would have, let's say, GDP per capita, and it's a number, right? Now, for you, this will be y, okay? This will be your y variable, okay? And suppose you are doing something like this. Suppose that you are taking the natural logarithm. First, let's do this. So this will be your variable yt, okay? And you may imagine yt is growing at this rate beta, okay? Now, what you can do here is this with that data for Turkey, right? So first, extend this model with a random term, okay? Suppose that there is this error term ut, okay? And you can imagine that ut is distributed as a normal variable, okay, with some variance, okay? Now, this is your model, right? And what you want to do is to find this growth rate, okay? Here's the trick. Suppose that you take the natural logarithms of both sides. Suppose that in column D, let's say, you are taking the natural logarithm of yt, right? So you have equals ln b2, right? b2 is here, okay? So you can find all the logarithmic levels, okay? Now, what happens to your model? Well, you have ln y0, okay, plus, careful, t times ln 1 plus beta, right? T times ln 1 plus beta plus ut. Now, what is that? What do you see here? This one. What do you see here? Speak up. What do you see there? It's a regression, right? Remember from econometrics, it's a regression. There is, so let me rewrite it. So if you imagine this is let's say dependent variable, this is a intercept coefficient, this is slope coefficient, this is independent variable, and this is the error term, right? Now, careful. Your variable was growing exponentially, right? Your variable is growing exponentially. So if you take the logarithm if you take the natural logarithm, it becomes linear. Okay? So the model tells you that at the rate beta, this variable will exhibit exponential growth, so its logarithm will be linear. So the slope here, okay, so if you look at the data, you will see something like this. Okay. If you look at the data of LNYT, you're going to see something like this. And then when you fit this regression, you're going to find a slope coefficient, an intercept coefficient, oops, and a slope coefficient. Okay. So through this, you're going to find Y0 hat. This is simply by OLS. Okay. You're going to find beta hat, and you're going to find UT hat. Okay. So what I just showed you is to calculate the long-run growth rate of an economy. So as economists, if at some point in your career, if somebody asks you how do you find long-run growth rate of an economy, you can show him or her this. Okay, that's how you find it, very simply. Is it too simple? Well, yes, of course. As you know, any model is a simplification. So we abstracted from many other things about growth, and we just said, okay, in the long run, this economy grows, right? So let's find that very long run trend growth rate, okay, starting at 1923. Okay. So now actually you can go to Madison website or you can download the Madison data, and you can do exactly as I described here, and you find beta. And beta will be in the annual data, it will be around 2.5. I mean, it will be between 2.5% and 3%. Okay, for Turkey. For US, it will be a little bit lower, around 2%. For Japan, I would imagine it will be slightly larger. Okay. And so on and so forth. So you can do that for any country in the world that is in the Madison website, all right, or the Madison data. Okay. So if you are interested in such stuff, these are the simple stuff that you can do in Excel and eViews and Gretel and whatever econometric software you're using, Stata, R. You can do such stuff, and that's pretty interesting. Okay. Now let me stop for a moment and answer your questions if you have any, or respond to your comments. Nothing? Okay. All right. So let me just continue then. Now, up to this point, so for today, I told you that we're going to talk about an analytical framework, right? So one part of it was the, discrete time, continuous time differences, defining growth rates, differential equations. Okay, and we covered these things. Now, the last task will be the idea of production function, okay? And of course, you know what a production function is, right? But we're going to be using the production function framework as one of the central tenets of this course, okay? So I want you to get a very firm understanding of this toolkit. All right. So let's start. Let me just quickly write this. Now, when I write something like this, obviously, you start thinking about, well, Y is output, right? It's the flow of output. K is capital stock, the entire collection of machines, tools, vehicles, bridges, roads, whatever you have, the tangible stuff that you use to produce other stuff. L, well, this is human labor, right? And A is technology, and there could be some other factors of production, right? So once F is a production function, of course, well, this will be output because output will be depending on inputs, okay? Now for the rest of the semester, such a production function will be the central element of our discussions, okay? Now let's write some production functions. Now the simplest production function that you can write, I believe, is something like this. There's output, and there is some constant productivity here, and there is raw labor, okay? So alpha is constant, and L is raw labor or unskilled labor, okay? And Y is, of course, output. Okay. So what do you have here? Well, marginal productivity is constant. Average productivity is the same, right? So if you want to draw this production function, it is just a linear production function, right? And here, of course, you also have, when you write this as a function, you realize that F0 is 0. Okay, so here labor is an essential input. Okay. Now this is possibly the simplest production function you're gonna have, right? Because in the real world, you know that there are machines, there's land, there's technology, there's human capital, different types of workers, different types of robots, right? So because when you say labor now in the 21st century, you have to be very careful. There's human labor and there's robot labor, right? Things like that. Now let's write another one, another familiar one. Okay. So you have, let's say, YT as a function of KT and LT, and it is written in this way. You have alpha KT plus beta LT. Now alpha and beta are both positive, okay? But now you have two arguments, right? This is capital stock, and this is labor again. You may imagine this as raw labor or unskilled labor, okay? So obviously, this production function has an interesting property. Why? Because here the isoproduct lines are linear, right? Remember this from micro. So there's these isoproduct lines, right? So if you think about it, there's LT here and KT here, and there are some isoproduct lines, each corresponding to some output level, right? So this is for, let's say, Y0, this is for Y1 greater than Y0, and this is for Y2 greater than Y1, right? And that goes on like this, okay? So these are isoproduct lines, and also you can imagine drawing this in three-dimensional space, okay? In three-dimensional space, right? So you have LT here, KT here, and F, KT, LT here, and obviously it will be what? It will be like a you know, a surface, a plane, right? So how do I do that? Well, at 0, we know that it is 0. Then from that point on, it will be like so it will be like a plane. How do I do that? So it will be like a plane. Okay. Yeah, that was not very well. I'm sorry, but you got what I mean, right? So for each L and K, there is a particular production level, okay, and it's here. And all of these points defines you a plane, okay? Now, let's do another one. I can write something like this, which I am sure you are again familiar with. Okay, so this is almost all the time called Leontief production function, right? And the isoproduct lines are kinked, right? The isoproduct lines are kinked. Why? Because we have the complementarity. Okay, so there is this line here. Okay, so that depends on alpha and beta. And then you have the isoproduct lines. Okay, now here, this is the Leontief technology. Okay, so this is Y0, this is Y1 greater than Y0, this is Y2 greater than Y1, and obviously in equilibrium, you want to equate these. Okay, so you also have Cobb-Douglas, right? For two argument production functions, you have the Cobb-Douglas production function, which you can write simply as this. Okay, so this is Cobb and Douglas, 1928, I suppose. Okay. Now, all these are, you know, the Leontief, the linear, All these are part of a general class of production functions, what we call the constant elasticity of substitution production function, okay? And it looks like this. Okay, so here alpha is called the shear parameter, okay, and rho is the curvature. Now rho takes values between -infinity and 1, okay, -infinity and 1, and sigma is defined as 1/1 minus rho, okay. This is the elasticity of substitution. Substitution of what? Substitution of capital and labor. Okay. And if sigma is equal to 1, sorry, if rho is equal to 1, sigma goes to positive infinity, right? Perfect substitutes. If sigma goes to negative infinity, sorry, rho goes to negative infinity, sigma goes to 0. Perfect complements. Oh, okay. We have to take a break. So let's meet at 250. All right. 250. I will see you at 250. Okay. Bye bye.